Notice how the oxygen on the water molecules here is attaching to the cation and pulling that off into the solution. And then you've got the hydrogens from other water molecules which are attaching to the anion and pulling the anion out into the solution. And so this is basically how salts are dissolved through water. The reason we use the term electrolyte for these ionic compounds that dissolve into solution is once they're in their ion form in the water, if you wanted to, you could pass an electric current through it. And it's the presence of these ions that allows essentially the flow of electrons to pass through, thus the name electrolyte. You need to memorize the 7 strong acids, and we will assume that those are strong electrolytes, meaning they will 100% ionize and form, obviously, ions in the solution. If it's not one of the 7 strong acids that you've memorized, you're going to assume that it's a weak acid. You have to memorize these rules, or else you're not going to be able to predict whether or not precipitate would form in a particular reaction. And, a way to tell this is if you see 2 reactants that are both aqueous, what you want to do is switch the cations, and then after you've switched the cations, use your solubility rules to predict whether or not something would precipitate out. All we're doing here with the ionic equation, or as it's sometimes referred to as the complete ionic equation, is we are taking everything that was present in the initial equation that was designated as AQ, so aqueous, and we are splitting it up and writing it as the ions are. And this is a more accurate picture of what's actually happening in the solution. Be careful when you're doing this to notice any subscripts. For example, if you were to have Na2CO3, so you're dealing with sodium carbonate, and you were to represent that in the complete ionic form, then you should have 2 now as a coefficient in front of the Na plus AQ, because for every mole of sodium carbonate that dissociates, you get 2 moles of the sodium ion. So for an equation to actually represent a reaction, then something new must be created. And so when you're talking about these neutralization reactions, the thing that's actually being formed is water. And we say that it's a salt in a water that's formed, when in reality the salt is just aqueous. And so you'll notice that in this equation the sodium was aqueous beforehand, and so was the acetate. So really the only thing that's actually being formed here is water. And that's going to be your net ionic equation anytime you add an acid to a base. So predicting products for gas-forming reactions, this can be kind of tricky, and really the best way to go about it is just to memorize some of these basic rules here that are outlined in the next few slides. So like it says here, when a carbonate or bicarbonate interacts with an acid, essentially a hydrogen ion, what you're going to get is carbon dioxide, salt, and water. And for both of these, you'll notice that the carbonate has gone from, you've got the CO3, and then the gas being produced has 1 less oxygen, and that's because of the production of water. So we have a similar thing here when we have sulfates or sulfites. We've got them reacting with an acid, and then your product is sulfur dioxide. Again, what we've got is water being formed, and therefore the product gas has 1 less oxygen than what your initial ionic compound had. Very important to memorize these rules for assigning oxidation numbers, because the majority of redox reactions that we look at are not going to be as simple as something like sodium metal added to chlorine gas yields sodium chloride, where it's a clear redox. A lot of times you might have multiple molecular species present, and the only way that you're going to be able to track whether or not redox actually happened is whether or not you can assign oxidation numbers to all of the substances both before and after, and then see if the oxidation numbers have changed over the course of the reaction. You can think of this activity series of the metals in this way. Since the most active metals are at the top, lithium is going to reduce the ion of any metal below it. So if I place lithium metal in a solution of any of these other ions below it, then what you're going to have happen is that metal, the ion, below lithium, its ion would be reduced and the lithium would be oxidized. And then of course you have what's known as the noble metals there at the bottom, platinum, gold, and those are not going to be oxidized regardless of whatever solution you place them in. And that's no coincidence that those are the metals that we like to use for our jewelry. You don't want your gold ring or watch sitting there reacting with the atmosphere while it's on your hand. So remember, when we're creating these solutions, that molarity is an expression of concentration, but it's moles of the solute per liter of solution. So since it's saying liter of solution, we have to take into account the volume that was displaced by adding the salt, which is why you have to use a volumetric flask when you're creating these solutions. You cannot say, for example, if you wanted to make a liter of 1 molar sodium chloride, you could not do that by just saying, well, a mole of sodium chloride would be around 58.45 grams, and so I could just dissolve 58.45 grams into 1 liter of water. It's not going to work, because that volume is actually going to be larger than a liter because of like I said, the volume that was displaced just from the presence of the salt. So you got to measure out the 58.45 grams, place it in the volumetric flask, and then we're going to add water until it gets right up to the mark of 1 liter. So just like density was a conversion factor for us in Chapter 2, in these type of problems, when you see molarity, when I read 0.500 molar sodium sulfate, I'm going to know that at some point in this calculation, I'm going to have to use that and sort of unpack it as 0.5 moles of sodium sulfate over 1 liter of solution. And since the question is asking me to convert to grams of sodium sulfate, and I know that I'm starting with 0.350 liters of this solution, then that's exactly what I'm going to do. I'm going to take the 0.350 liters and use that as the starting point in your conversion, place it in the upper left-hand corner, and then use the molarity as the conversion factor, which will ultimately allow you to go from moles of sodium sulfate to grams. So this is a neutralization reaction, and this is very much analogous to what we did earlier, where we were just doing, like in Chapter 1 or 2, where we would go from, let's say, you have a question that says, how many grams of nitrogen would be needed to react with 27 grams of hydrogen to make 58 grams of NH3. The only difference between questions like that in Chapter 1 and 2 and what we have here is we're given different amounts of the reactants, but you're still going to have a balanced equation, and you're still going to have to go from the volume of the molar concentration of the nitric acid, and it's still going to be a mole to mole. So you need a balanced equation, and then you need to take the volume of your known concentration, convert that volume to liters, and that gets you to moles right there. And then once you're to moles, it's the same game that we played in Chapter 1 and 2, where we have to go from moles of the nitric acid to moles of the calcium hydroxide. And again, that's going to be dictated by the balanced equation. But then once you get to moles of calcium hydroxide, then it's just a mole to gram conversion to finish the problem. A little bit of review here of everything we've covered thus far in the class.